300 feet above the canyon floor, standing on a wooden beam 6 inches wide, no safety harness, no railing, just you, a hammer, and the knowledge that one wrong step means a fall that will kill you before you hit the ground. And you're not alone up here. There are dozens of other workers, all of them balancing on timber frameworks that sway slightly in the wind, building a bridge that will carry locomotives weighing 100 tons across a canyon so deep you can barely see the bottom. The entire structure is made from trees, local timber cut from surrounding forests, shaped with hand tools, assembled piece by piece into towers that rise higher than most buildings of the era. And when it's done, trains will cross it every day. Passengers will look out windows at a drop that makes them dizzy. Engineers will throttle their locomotives carefully, feeling the structure flex under the weight, and everyone will wonder, how is this possible? How can wood hold up a train 300 feet in the air? This was America in the late 1800s, and railroads needed to cross canyons, ravines, and river gorges that were too deep to fill and too wide to span with conventional bridges. The solution was the timber trestle, a framework of wooden posts and beams rising from the canyon floor or built on the canyon walls, creating a platform high in the air for the railroad tracks. These weren't small structures. The tallest wooden railroad trestles reached over 300 feet, higher than a 30-story building. They stretched hundreds or even thousands of feet horizontally, and they were made entirely from wood, pine, fir, cedar, on whatever grew nearby, held together with wooden joints, iron bolts, and an engineering understanding that pushed wood to its absolute limits. Could you really build a 300-foot tower entirely from wood? Could timber frameworks support the weight of locomotives and freight cars? Could you maintain such structures in mountain weather, snow, wind, ice, and keep them safe for daily train traffic? The answer is yes. The evidence exists in photographs showing these incredible structures, in engineering drawings preserved in railroad archives, and in a few surviving trestles that still stand, monuments to what could be accomplished with timber, skill, and determination. Before we get to the tallest trestles, you need to understand the basic engineering of timber trestle construction. Because these weren't just piles of wood stacked up randomly. They were carefully engineered structures designed to support specific loads under specific conditions, built with techniques that had been refined over decades of railroad construction. A railroad trestle is essentially a series of vertical towers, called bents, supporting horizontal beams, called stringers, on which the railroad track is laid. The simplest trestle is a row of identical bents, each one supporting its section of track. But as trestles get taller, the engineering becomes more complex. You can't just make the bents taller. The loading changes. The wind loads increase. The structure becomes more flexible. Tall trestles required sophisticated bracing, careful attention to joint design, and an understanding of structural behavior that went beyond simple stacking of timbers. The basic bent for a timber trestle consisted of 4 vertical posts connected by horizontal and diagonal bracing. The posts were typically 12 to 18 inches square, made from solid timber, usually a single tree trunk squared with axes and adzes. The posts would rest on foundations, sometimes stone footings, sometimes just flat rocks or compacted earth in remote locations. The horizontal bracing connected the posts at regular intervals up the height. The diagonal bracing prevented the bent from racking, twisting side to side, under load. For a low trestle, 20 or 30 feet high, a single bent with 4 posts might be sufficient. But for a tall trestle, the engineering was more complex. The bents would be built in tiers. You'd build a base tier perhaps 30 feet tall. On top of that, you'd build another tier. And another. Each tier was essentially a complete bent resting on the tier below. The tallest trestles might have 4 or 5 tiers rising over 100 feet. The lumber requirements for a tall trestle were staggering. A trestle 300 feet tall and 1,000 feet long might use 2 million board feet of timber, equivalent to about 400 large trees. All of this timber had to be cut from local forests, transported to the site, shaped to specifications, and assembled at height. For a remote trestle in mountain country, getting the timber to the site was often as difficult as the actual construction. The selection of timber for a tall trestle was critical. Not just any tree would work. The timber needed to be straight-grained, unfree of large knots, and from a species strong enough to support the loads. In the West, Douglas fir was preferred, strong, relatively straight, and available in large sizes. In the East, oak and chestnut were used. In the South, longleaf pine was common, but often the engineers had to use whatever was locally available, which sometimes meant using species that were less than ideal. The size requirements were substantial. A post for the lower tiers of a tall trestle needed to be at least 12 inches square and might be 20 to 30 feet long. That requires a tree that's at least 18 inches in diameter at breast height and straight for at least 30 feet of its length. Finding trees that met these requirements meant scouring forests for specific specimens. In virgin timber regions, suitable trees were abundant. But as forests near railroads were logged out, finding adequate timber became progressively more difficult. The cutting and preparation of timber for a tall trestle followed logging procedures, but with more stringent quality control. A logging crew would go into the forest near the trestle site. They'd mark suitable trees, fell them, delimb them, and cut them to required lengths. Then teams of oxen or horses would drag the logs to the trestle construction site. The hauling distances could be significant, miles through forest to reach the site. Each log had to be dragged over rough terrain, often up or down steep slopes. At the construction site, the logs would be squared using broad axes. A rough log would be transformed into a precisely dimensioned beam. The squaring was done by skilled hewers who could create flat surfaces accurate to within a quarter inch over 20 feet of length. This precision was necessary because the timbers had to fit together in mortise and tenon joints that required tight tolerances. The shaping of joints was even more exacting. The mortises, rectangular slots cut into timbers, had to be precisely sized to receive tenons cut on the ends of other timbers. A mortise might be 6 inches wide, 8 inches tall, and 6 inches deep, cut through a 12-inch square post. Getting these dimensions exact using hand tools required considerable skill. The work was done with augers to drill out most of the waste wood, then chisels to square the corners and true the surfaces. The logistics of having the right timber at the right place at the right time during construction was a major management challenge. A tall trestle might require hundreds of different timber pieces, each one cut to specific dimensions for a specific location in the structure. Too much timber on site and you're wasting space and money. Too little and construction stops while workers wait for material. The construction superintendent had to plan the timber delivery sequence carefully, coordinating the logging crews, the hauling teams, and the construction schedule. The construction process for a tall trestle started with the foundations. Workers would clear the site, removing vegetation and loose material down to solid ground or rock. Then they'd set foundation stones or build crib work, stack timbers filled with rock to create level bearing surfaces for the bent posts. Getting foundations right was critical. An unstable foundation would cause the entire bent to lean or settle unevenly, potentially leading to failure. With foundations in place, the first tier of bents would be erected. The vertical posts would be positioned on the foundations and temporarily braced to hold them vertical. Then the horizontal and diagonal bracing would be installed, connecting the posts and creating a rigid structure. This work was done from the ground for the first tier, which made it relatively straightforward, though still requiring considerable skill and coordination. Once the first tier was complete, the second tier would be built on top of it. This is where the work became dangerous. Workers had to climb onto the first tier to build the second. They'd be working 30 or 40 feet in the air on narrow timbers. The techniques for working at height were crude by modern standards. Workers would walk on the horizontal bracing timbers, maintaining balance without safety equipment. They'd carry tools, hammers, saws, augers, while navigating the structure. And they'd lift heavy timbers into position using rope and block and tackle systems. The lifting of large timbers to upper tiers required coordination and muscle power. A timber for an upper tier post might be 18 feet long and 12 inches square. weighing several hundred pounds. Workers on the ground would attach ropes to the timber. Workers on the structure above would haul on the ropes, pulling the timber up, hand over hand. Once the timber reached the correct height, other workers would guide it into position and secure it temporarily while joints were cut and the timber was permanently installed. The joint work on a timber trestle was skilled carpentry done in difficult conditions. The posts and bracing had to fit together precisely. The standard joint was a mortise and tenon, a slot cut into one timber, a projecting tab cut on another timber, the two fitting together tightly. These joints had to be cut accurately, or they wouldn't fit, and cutting them while standing on narrow beams high in the air required both skill and nerve. The securing of joints used a combination of wooden pegs, iron bolts, and iron straps. Wooden pegs, trunnels, were driven through drilled holes to lock mortise and tenon joints. Iron bolts provided additional strength and prevented joints from pulling apart under stress. Iron straps reinforced critical connections, particularly where diagonal bracing met posts. The ironwork had to be fabricated on the ground and hauled up to the installation point, adding another layer of complexity to the construction. As the trestle grew taller, every aspect of the work became more difficult and more dangerous. At 100 feet, the wind becomes a factor. The structure sways slightly. Workers have to adjust their balance constantly. Dropping a tool means it falls 100 feet. If it hits someone below, it could kill them. At 200 feet, the psychological impact of the height becomes significant. Workers who'd been comfortable at 100 feet found 200 feet terrifying. Not everyone could handle it. Some workers would climb to height, look down, and freeze. They'd have to be talked down by other workers. The tallest wooden railroad trestle ever built in the United States was probably the Cascade Bridge on the Northern Pacific Railroad in Washington State. The original trestle, built in 1887, was not exceptionally tall, about 90 feet at its highest point. But in 1892, the Northern Pacific built a temporary detour trestle while they constructed a tunnel through the Cascade Mountains. This temporary trestle was over 200 feet tall at its highest point and stretched for nearly a mile. It was used for less than a year before the tunnel opened, then dismantled. But during its brief existence, it was one of the most impressive timber trestles ever constructed. And another notable tall trestle was the trestle at Secrettown in California, built by the Central Pacific Railroad in the 1860s. This trestle crossed a ravine about 150 feet deep. It was built from local timber, mostly Douglas fir, and used approximately 300,000 board feet of lumber. The construction took about 3 months and employed about 100 workers. The trestle remained in service for over 20 years before being filled with rock and earth to create a conventional embankment. The Dale Creek Bridge in Wyoming, built by the Union Pacific in 1868, was 126 feet high at its tallest point and 650 feet long. It was built from timber cut from nearby forests, mostly lodgepole pine, which was not ideal for heavy construction but was what was available. While the trestle's construction took about 30 days with a crew of approximately 500 workers, it remained in service for 13 years, carrying thousands of trains across the canyon, before being replaced with an iron bridge in 1881. The Pecos River Bridge in Texas, built by the Southern Pacific Railroad in 1882, was a massive structure, 321 feet above the river at its highest point and over 2,000 feet long. While it was technically a combination of iron and wood construction, the approach trestles were entirely wooden and reached heights of over 200 feet. These wooden sections used approximately 4 million board feet of timber, representing the clearing of nearly 1,000 acres of forest. The construction took 14 months and employed up to 800 workers at its peak. The Columbia River Gorge presented numerous challenges for railroad construction, and multiple tall wooden trestles were built along both the Oregon and Washington shores. One of the tallest was at Shell Rock Mountain, where the Oregon Railway and Navigation Company built a trestle in 1883 that was approximately 180 feet high and 800 feet long. The construction site was difficult to access, located on a steep mountainside with limited flat ground for staging materials. Timber had to be hauled along precarious temporary roads. Workers camped in tents on narrow terraces cut into the hillside. The construction took 6 months despite the relatively modest size of the structure, entirely due to the difficult access and working conditions. The Muir Trestle on the Santa Cruz and Felton Railroad in California, built in 1875, and crossed a ravine about 150 feet deep in heavily forested terrain. What made this trestle remarkable was that it was built almost entirely from redwood, old-growth redwood cut from the very forest the trestle crossed through. Redwood's natural rot resistance made it an excellent choice for trestle construction, and the Muir Trestle lasted over 40 years before being replaced, far longer than most wooden trestles. In Montana, the Montana Central Railway built a series of tall trestles crossing the deep coulees of the high plains. The tallest, near Great Falls, was approximately 190 feet high and built from lodgepole pine cut from mountain forests 50 miles away. The hauling of timber to the site took nearly as long as the construction itself. Teams of oxen moved loads of timber along primitive roads, making the journey in a week or more per round trip. The construction required the steady flow of timber for 6 months to build the trestle, which entered service in 1889. The Virginia and Truckee Railroad in Nevada built multiple tall trestles in the 1870s to navigate the rugged terrain of the Sierra Nevada foothills. The Crown Point Trestle was about 170 feet high and notable for its elaborate bracing pattern designed to handle the heavy ore trains the railroad carried. The engineering was more sophisticated than typical wooden trestles of the era, with double-tier construction and reinforced joints using iron strapping. This extra engineering allowed the trestle to carry loads that would have destroyed conventional wooden structures. The workers who built these tall trestles were a mix of experienced carpenters, general laborers, and men who'd never done construction work before but needed jobs. The pay was good by the standards of the time, $3 to $5 per day for skilled workers, $2 to $3 for laborers. But the work was dangerous enough that many men wouldn't do it at any price. The crews that specialized in tall trestle work developed reputations. Railroad companies would seek out these crews for difficult projects because they knew the men could handle the height and the danger. The psychological challenge of working at extreme heights cannot be overstated. At ground level, carpentry work is straightforward. You stand on solid ground. You manipulate your tools, you cut and fit joints. At 200 feet in the air, standing on a 6-inch wide beam with a 100-foot drop beneath you, every action requires conscious thought about balance and positioning. Workers learn to move deliberately, never rushing, always maintaining 3 points of contact with the structure. One hand on a timber, one foot planted firmly, then move the other foot. Then shift the hand. Never make a sudden movement. Never look down unless necessary. The physical adaptations workers developed were remarkable. Men who worked on tall trestles for months would develop extraordinary balance and spatial awareness. They could walk along narrow beams with the same confidence most people have walking on a sidewalk. They could carry heavy tools while maintaining balance. They could work with both hands while their feet were positioned on separate beams. But this skill took time to develop, and new workers were particularly vulnerable to accidents during their first weeks on a tall trestle. The training for new workers was minimal and brutal. An experienced worker would demonstrate the basic safety rules. Always maintain contact with the structure. Watch where you place your feet. Move slowly and deliberately. Then the new worker would climb the structure with supervision. Some men made it to the first tier without problems. Others would get 30 feet up and freeze, unable to climb higher or descend. These men would be sent to ground crew work. Those who made it to full height on their first climb would be put to work immediately. The only real training was doing the work under the supervision of experienced workers who would intervene if they saw someone doing something dangerous. Among the trestle builders was a man named Daniel O'Brien, an Irishman who worked on trestle construction in the Western Territories from 1867 to 1885. O'Brien started as a laborer and worked his way up to foreman, supervising crews on some of the tallest trestles built during that era. His descendants preserved some of his letters, which described the work and the conditions. from a letter O'Brien wrote to his brother in Ireland in 1871. "We are building a trestle across a canyon so deep I cannot see the bottom. The work requires climbing to heights that make my stomach turn. I am responsible for a crew of 30 men, all of us working on timbers 200 feet above the ground. Yesterday, a worker named Thomas Brennan fell from the upper tier. He dropped over 100 feet and died instantly. We retrieved his body and continued working. There was nothing else to be done. The trestle must be completed on schedule." O'Brien's letter describes another incident from 1873. "The wind is constant at this height. It pushes against you as you work. You must brace yourself constantly. Today, a gust caught a timber we were lifting and swung it like a pendulum. 3 men were nearly knocked off the structure. One man, Patrick Doyle, was struck by the swinging timber and broke his arm. He climbed down one-handed and was taken to the nearest town for treatment. The rest of us continued. We cannot stop for injuries unless someone is killed." A third letter from O'Brien, written in 1875, describes the psychological toll. "I've been working on tall trestles for 8 years now. I've seen perhaps 20 men fall to their deaths, and I have seen many more injured. Each time a man falls, I wonder if I will be next. But the pay is good, and I have a family to support in Omaha. So I continue climbing to heights that no man should climb, trusting in Providence and in my own careful attention to what I am doing." O'Brien himself was killed in 1885 when a trestle he was supervising partially collapsed during construction. The investigation determined that a foundation had been improperly set on unstable ground. When a loaded tier was placed on the foundation, it shifted, the post tilted, and the entire bent came down. O'Brien and 4 workers were on the structure when it fell. All 5 were killed. O'Brien was 47 years old. His widow received no compensation beyond his final pay. Another documented trestle worker was James Chen, a Chinese immigrant who worked on trestle construction for the Central Pacific Railroad in the 1860s. Chen was part of a crew of Chinese workers who built several of the tall trestles in the Sierra Nevada. His experiences were recorded secondhand in the journal of a railroad engineer who worked with him, as Chen himself left no written record. According to the engineer's journal, Chen was fearless at height. He would walk along the narrowest beams without apparent concern. He was particularly skilled at the dangerous work of positioning the upper tier posts, work that required climbing onto timbers that weren't yet fully secured and maneuvering heavy posts into position. The engineer wrote, "Chen moves on the structure like a cat. I have seen him climb to the top of a partially completed bent, balance on a single post while other workers lift a new post to him, then guide the post into position while maintaining his precarious balance. It is extraordinary to watch and terrifying to think about." Chen survived his trestle work and later worked on railroad maintenance, but the engineer's journal notes that many of Chen's co-workers were killed in construction accidents. The Chinese workers, the engineer observed, were often assigned the most dangerous work because railroad supervisors considered them expendable. The death rate among Chinese trestle workers was significantly higher than among white workers, not because they were less skilled, but because they were deliberately placed in more hazardous positions. The fatality rate for tall trestle construction is difficult to establish precisely because records are incomplete. But, based on available documentation, approximately 2 to 5% of workers on tall trestle projects were killed in falls or construction accidents. For a project employing 100 workers over several months, that might mean 2 to 5 deaths. The deaths were considered acceptable losses, tragic but inevitable given the nature of the work. The experience of crossing a tall trestle as a train passenger was memorable. The train would approach the trestle, and passengers looking ahead would see what appeared to be a delicate framework of timber rising impossibly high. As the train moved onto the trestle, passengers could look out the windows and see nothing but air beneath them. The trestle would flex slightly under the train's weight, a sensation passengers could feel. The structure would creak and groan. Some passengers found the experience terrifying and would close their eyes or move to the center of the car where they couldn't see out the windows. A traveler named Harriet Bishop, who crossed the Dale Creek Bridge in 1870, wrote in her journal, "We approached a wooden bridge of astounding height. The engineer slowed the train to a crawl. As we moved onto the bridge, I looked out the window and immediately regretted it. We were suspended hundreds of feet above a rocky canyon. The bridge swayed noticeably. I could see between the wooden timbers to the ground far below. Other passengers were praying aloud. The crossing took several minutes that felt like hours. When we reached solid ground on the other side, there was audible relief from everyone in the car. Railroad companies were aware of passenger anxiety about tall trestles and tried to minimize it. Trains would cross trestles slowly, often at 5 to 10 miles per hour instead of the normal 20 to 30. This was ostensibly for safety. Going too fast could damage the trestle or cause derailment, but it also reduced the swaying and flexing that passengers found disturbing. Some railroads would provide curtains that could be pulled across windows during trestle crossings, allowing nervous passengers to avoid seeing the drop. The maintenance of tall wooden trestles was constant and demanding. Wood exposed to weather deteriorates. At high altitude or in mountain environments, the weather was particularly harsh. Freeze-thaw cycles would crack timbers. Snow loads would stress the structure. Wind would work at joints, gradually loosening them. A tall trestle required regular inspection and ongoing repair to remain safe. Railroad companies employed trestle inspectors who would walk the structure regularly looking for damage. Inspecting a tall trestle meant climbing to the top and examining every tier, every joint, every timber. It was dangerous work in itself. The inspectors would mark damaged components for replacement or repair. Then maintenance crews would climb the structure with tools and materials to do the work. The inspection procedure was systematic. An inspector would start at one end of the trestle and work methodically through the structure. At each bend, he'd examine the post for cracks, checks, or signs of rot. But he'd test wear joints by trying to move them. A tight joint was good, a loose joint needed attention. He'd look for rust on iron hardware, which could indicate water penetration. He'd examine the foundations for settling or erosion, and he'd check the overall geometry of the structure, looking for bends that had shifted out of plumb. The tools for inspection were simple but effective. A hammer to tap on timbers, solid wood sounds different than wood with internal rot, an awl or ice pick to probe suspect areas. The tool would sink into rotten wood but not into sound wood, a measuring tape to check for displacement or settling, and a notebook to record findings. An experienced inspector could evaluate a 100-foot trestle in a day, making notes of every defect that needed attention. The marking system was critical to efficient maintenance. The inspector would use chalk or paint to mark timbers that needed work. A single mark might mean minor repair. A double mark meant replacement required. An X mark meant the timber was critically damaged and needed immediate attention. The maintenance crew would follow behind the inspector, working from the marks, addressing the most critical issues first. The replacement of a damaged timber in a tall trestle was complex. If the timber was part of the load-bearing structure, a post or major bracing member, you couldn't just remove it without support. The procedure was to install temporary supports to carry the load, then remove the damaged timber, install the new timber, and remove the temporary supports. This work had to be done carefully and precisely. A mistake could cause structural failure and collapse. The temporary supports were typically screw jacks, mechanical jacks that could be positioned under the load and extended to take weight off the component being replaced. Workers would install multiple jacks, slowly transferring load from the damaged timber to the jacks. Then they'd remove the damaged timber, cutting away the old mortise and tenon joints, extracting the timber piece by piece if necessary. With the old timber removed, they'd install the new one, cutting new joints, positioning it precisely, and securing it with bolts and straps. Finally, they'd slowly transfer load back from the jacks to the new timber, watching carefully for any signs of problem. The entire process for replacing a single major timber might take 2 or 3 days. The frequency of maintenance varied by climate and traffic. A trestle in a harsh mountain climate might need major work every year. A trestle in a dry, temperate climate might go several years between major maintenance periods. But all trestles needed constant attention. Small repairs were ongoing, tightening bolts, replacing individual boards on the deck, clearing drainage, painting iron hardware to prevent rust. A maintenance crew might spend 1 day per week on a major trestle just doing routine work. There were instances of tall trestles collapsing, sometimes with trains on them. In 1875, a trestle on the lakeshore and Michigan Southern Railway in Ohio collapsed as a train was crossing. The trestle was about 70 feet tall and had been in service for 8 years. An investigation determined that a key support timber had rotted internally without visible exterior damage. When the train's weight loaded the structure, the rotten timber failed, the tier collapsed, and the train fell with it. 11 people were killed, including the engineer and fireman, and several passengers. The collapse prompted railroad companies to increase inspection frequency and to be more aggressive about replacing timbers that showed any signs of deterioration. But inspections were imperfect. Internal rot could be impossible to detect without drilling into the timber or cutting it open, procedures that weren't practical for every timber in a large trestle. The industry accepted a certain level of risk as inherent in operating tall wooden trestles. The engineering analysis of trestle failures revealed patterns. Most collapses occurred during the winter months when snow loads added significant weight to the structure. A foot of wet snow on the deck of a large trestle could add hundreds of tons of load. If the trestle had deteriorated timbers that were marginal but still functional under normal loads, the addition of snow load could push them past their capacity. Wind was another significant factor. Tall trestles acted like sails, catching wind and developing substantial lateral loads. The engineering for tall trestles had to account for wind, which meant extensive diagonal bracing. But wind patterns in canyons could be unpredictable. A canyon might funnel wind, creating velocities much higher than in open terrain. A trestle designed for winds of 50 miles per hour might encounter gusts of 80 or 90 miles per hour during storms, potentially exceeding its design capacity. The most catastrophic tall trestle failure in American history occurred on the Eden Mills Trestle in Vermont in 1887. The trestle was approximately 100 feet high and 600 feet long. On a winter day in February, a passenger train was crossing when the trestle collapsed. The investigation later determined that ice had formed on the structure during previous days, adding significant weight. When the train loaded the structure, several key posts failed simultaneously. They'd been weakened by rot that wasn't visible through the ice coating. The entire central section of the trestle collapsed, dropping 3 cars into the ravine. 37 people were killed, making it one of the deadliest railroad disasters of that era. The Eden Mills disaster led to significant changes in trestle inspection practices. Railroads began requiring winter inspections after ice storms to assess ice loading. They implemented policies for train speed restrictions during high winds. And they accelerated the replacement of wooden trestles with iron structures, recognizing that wood's vulnerability to deterioration created unacceptable risk on high traffic lines. Another significant collapse occurred on the Big Creek Trestle in California in 1891. This trestle was approximately 180 feet high and had been in service for 12 years. A freight train was crossing when the trestle collapsed. The engineer, seeing the structure beginning to fail, accelerated in an attempt to get across before complete collapse. The locomotive made it to solid ground, but 2 freight cars were left on the collapsing trestle and fell with it. And the 2 brakemen riding those cars were killed. The investigation revealed that the foundation on one bent had been undermined by erosion, causing the bent to tilt progressively over several months until it finally failed catastrophically. The transition from wooden trestles to iron and steel structures came gradually in the late 1800s. Iron had advantages. It didn't rot, it could span longer distances with less material, it could be precisely engineered. But iron was expensive. For many railroads, particularly in the West where capital was limited, wooden trestles remained the practical choice for decades after iron alternatives became available. The replacement process was typically driven by the need for maintenance. When a wooden trestle reached the point where it needed major rebuilding after 15 or 20 years of service, the railroad would evaluate whether to rebuild in wood or replace with iron. If traffic had increased and the old wooden structure was no longer adequate, or if iron prices had come down enough to be affordable, the choice would be to replace with iron. But many wooden trestles were rebuilt in wood multiple times before finally being replaced with permanent structures. By 1900, most new railroad trestles were being built from iron or steel. The wooden trestle era was effectively over, though existing wooden trestles remained in service. Through the early 1900s, thousands of wooden trestles were still carrying trains across canyons and ravines, but they were gradually being replaced. The last major wooden railroad trestle in regular use in the United States was probably dismantled in the 1930s or 1940s, though some smaller trestles on logging railroads and industrial lines lasted into the 1950s. Today, very few tall wooden railroad trestles survive. Most were dismantled when replaced with permanent structures, and the timber was either sold as salvage or left to rot. The few survivors are mostly in remote locations or have been preserved as historical structures. The tallest surviving wooden trestle is probably the Kinzua Viaduct in Pennsylvania, though it was partially destroyed by a tornado in 2003. Even in its damaged state, it gives an impression of the scale and engineering of tall wooden trestles. Walking beneath a tall trestle, if you can find one, is an extraordinary experience. Looking up at the framework rising overhead, seeing the complexity of the bracing, the joints, the layers of construction, you get a sense of the engineering sophistication involved. And when you consider that this was all built by hand, by workers standing on narrow timbers hundreds of feet in the air, the achievement becomes even more remarkable. The tall wooden railroad trestles represent a specific moment in transportation history. They were necessary because railroads needed to cross deep canyons and couldn't afford permanent iron structures. They were possible because timber was available and workers were willing to risk their lives building them. They were temporary by intention, meant to last just long enough to justify their cost and allow time to build better replacements. But temporary turned out to mean decades in many cases. These wooden towers carried millions of passengers and billions of pounds of freight safely across impossibly deep canyons for years or decades before finally being replaced. The workers who built them, the Daniel O'Briens climbing to dizzying heights, the Thomas Brennans who fell to their deaths, the Patrick Doyles who were injured and continued working, they accomplished something that seems impossible when you see photographs of these structures. They built frameworks of timber 300 feet tall. They did it standing on narrow beams with no safety equipment. They lifted timbers weighing hundreds of pounds to heights where a fall would be fatal. And they did it knowing that people would die during construction, that the structures would flex and sway under train loads, that passengers would cross them in fear. But they built them anyway because the railroad had to cross the canyon, and wooden trestles were the only practical solution. The photographs that survive of these trestles are striking. The most common view is from below, looking up at the framework rising overhead, showing the complexity and height. But there are also photographs taken from the structure during construction, showing workers perched on beams hundreds of feet above the ground, and photographs of trains crossing, showing the locomotive and cars suspended in air on what appears to be an impossibly delicate wooden framework. These images capture both the engineering achievement and the vertigo-inducing reality of tall wooden trestles. If you ever get the chance to visit a surviving tall wooden trestle, take it. Stand at the base and look up. Try to imagine building that structure, one timber at a time, climbing higher with each tier. Imagine being on top, 300 feet in the air, balancing on a beam, while positioning another massive timber. Imagine a train crossing above you, the structure flexing and creaking under the weight, and consider that this was how railroads crossed canyons for decades, with wooden frameworks built by men with hand tools, rising higher than most people could imagine, carrying trains safely across spaces that should have been impassable. The tall wooden railroad trestles are gone now, mostly, dismantled and replaced, or collapsed and abandoned. But they were real. They carried real trains with real passengers across real canyons. They were built by real workers who climbed to terrifying heights and did precision carpentry work while standing on 6-inch beams with 100-foot drops beneath them. They represented the limits of what could be done with timber and determination and a willingness to accept risk. And they worked. For decades they worked. That's worth remembering.